everyone, and welcome to section 4.1 in Precalculus. Today we are going to study something that is probably new to everybody. It's going to seem a little challenging at first. Luckily, this is a video, so you can rewatch it if you need to. First, we're going to draw an angle in standard position. What that means is that the initial side is going to be here. And then it's going to rotate counterclockwise to get up to the angle. Think about a protractor. You may remember what a protractor looks like. It starts here at 0 and then it wraps around, and that's how you would measure an angle. So there's the little center of the protractor. This is called the initial side. Where it terminates is called the terminal side. And this point right there is called the vertex. The measure of an angle is determined by the amount of rotation from the initial side to the terminal side. There are two ways to measure angles. One is degree measure, which you guys are really familiar with. You know that one full revolution is 360 degrees. A half of a revolution, so halfway around the circle, is 180 degrees, which would mean that a quarter of the way around the circle is 90 degrees. And so 1 degree is literally 1/360th of a circle. But today I'm going to introduce you to something called radian measure. A radian is a little less than 60 degrees. And 1 full revolution is 2 pi. 1/2 revolution, so a full circle, is going to be 2 pi. I know it would be so convenient if 1 all the way around was pi, like an actual PIE pi, but it's not. It has very good reason why that's the way it is. But a half revolution is pi, which would mean a quarter of a revolution. It's not a quarter. I know that would be so nice. Is going to be pi halves. So I am going to quickly explain why that's true, because it might help some of you to remember it. It's not because somebody just arbitrarily picked those numbers. I don't know how many of you realize where pi comes from. You might know that pi is approximately 3.14, but I don't know that everybody that's listening today actually knows what even is pi. So pi is merely the ratio of a circumference of a circle to the diameter of that circle. You're probably watching this from home. If you look at any circle, if you have a circular table, if you have a circular coaster, if you have a circular pencil jar, a button, anything at all in your house, and you measure its circumference all the way around, and then you measure its diameter, every single time you do that, you measure the circumference and then the diameter. If you put them as a ratio, you're going to get 3.14. Point blah 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 blah. Like there's more to it, but approximately 3.14. So it doesn't matter if the circle is enormous or if the circle is tiny. The ratio of the circumference to the diameter is always 3.141. Like it keeps going, and somebody gave that the name pi. That's where it comes from. So because if we clear this fraction, pi times d is equal to the circumference. And you may remember that circumference, the formula for circumference is 2 pi r. That's where that comes from. Diameter is really the same as 2r. So 2 radiuses make the circumference, or 2 radiuses make the diameter. So see, 2 pi r, they're just written differently as 2 pi r. That's where that formula for circumference comes from. So why 2 pi? So if you had this arm, this radius, when you took it and you went all the way around the circle, you would get circumference. So what must be all the way around the circle? 2 pi. So it's not like somebody just arbitrarily said, let's call it 2 pi. It actually is 2 pi. So if you take the radius and you go all the way around 2 pi, you'll get that circumference. Okay, if you totally didn't understand what I said in the last minute, doesn't matter. Memorize this. 1 full revolution, 2 pi. Half revolution, pi. Quarter revolution, pi halves. So just like you've always known, not always, but for years have known 360, 180, and 90, now you have to know 2 pi, pi, and pi halves. There are 4 quadrants, same quadrants that we've always used, but just as a reminder, 1, 2, we do use Roman numerals to represent them, 3, and quadrant 4. So in degrees, this is something you're pretty familiar with, 240. You might think to yourself, okay, well, that's 180, so 240 must be somewhere around there. It might help if you knew that this was 270. So 240 is somewhere around there. That's how you would sketch the angle 240 degrees. You don't even have to draw the terminal side. This just would represent the angle 240. The problem is now we want to do things like 7 pi halves. So you might remember from a minute ago that pi halves is the same as 90 degrees, or that pi is the same as 180. So you, for a while, will probably be converting it in your head. But I'm going to just think of this as 3 pi and a half, right? 7 halves is the same as 3 and a half. So here's 2 of the pi's, right? There's all the way around is 2 pi. And then 3 pi would go around again. And then a half of a way around here. That's where I landed. But that's not how you draw an angle. So to draw the angle, you would just draw it right here. That's 7 pi halves. The last one, 2 pi thirds. So again, you're just thinking about the 2/3. Pi is halfway around. This is pi. Pi in 180 degrees, same. So you're doing 2/3 of the pi. So instead of going all the way over to the other side, you're doing 2/3. So I realize that this is really tricky. I did on Google Classroom post some blank circles that look like this. You might want to pull one of those up. It's not in your notes yet because technically we're not really using the unit circle yet. But I do think that this helps some people understand how this goes. So it's not actually presented in your book until section 2, and we're only in section 1, but I personally just like to introduce it here. If you want, you can just watch, or you can take one of the blank unit circle pages and try and get this. But I'm going to show you how it's easy to remember where everything is. So first, I'm going to label 0, the ones we just learned, pi halves, pi, and 3 pi halves. Now, this unit circle, even though we can't see it, I think I'm going to just put it in a nice soft yellow here. I'm going to add this. So is actually divided like a clock into 12ths, but nobody uses the yellow ones, or not, I shouldn't say nobody, but the yellow ones just aren't as commonly used, so we don't tend to draw them on our unit circle. But I think that just this once, to explain it, you'll better understand how it works. So this is pi divided by 12, pi 12ths. So remember, pi is halfway around, and I've broken it up into 12 pieces, 24 altogether. So this is pi 12ths. This is 2 pi 12ths, 3 pi 12ths, 4 pi 12ths, and, oops, got a little too close to the edge there, and 5 pi 12ths. So this one's 6/12. 6/12 is the same as 1/2, so I'm not going to label that one. 7 pi 12ths, 8 pi 12ths. I know. All right, some of you are already bored. 10 pi 12ths, a little faster, and 11 pi 12ths. And this one is 12/12, which is 1 whole, 12/12. All right, then we get 13/12, 14/12, 15/12, 16 twelfths, 17 pi twelfths, and 18 pi twelfths, which we reduce to 3 halves. 19 pi twelfths, 20 pi twelfths, 21 pi twelfths, 22 pi twelfths, and 23 pi twelfths. And the last one, of course, being 24 pi twelfths, which reduces to what? 2 pi. 24 over 12 is 2. So I put these in yellow, which is a little light and a little hard to read because they're not the ones I want to focus on. I want to focus on these other 3 branches. So let's do the one in the middle first. 3 twelfths is the same as pi fourths. So that's what everybody's going to call it. So this is 1/4, 2/4, which is the same as a half, but I'm not going to write it because a half is better. And then this one is 3 pi fourths. And then 4/4, which is 1. And then this one is 5/4, 5 pi fourths. 6/4, which I'm not going to relabel. I'm going to keep all the blue ones blue, and now I'm going to do the green ones green. So 6 pi fourths, which is better said as 3 pi halves, and then 7 pi fourths. So 21 over 12 reduces to 7 over 4. So 7 pi fourths is how we say it, by the way. 7 pi fourths. So there's all the fourths. So you can remember that the fourths are these lines right here. They're right in the middle. Those are going to be all your fourths. And now, so the blue ones are going to be here. The blue ones are kind of the main ones. They're called quadrantals because they're right on the quadrant. Okay, now I'm going to do the red ones. So I'm going to draw a red line right here. And think about this angle, which is going to be pi 6, as how far it is from the x-axis, which means it's going to correspond with this one. They're both the same distance as in terms of an angle away from the x-axis, which means this one is going to correlate, and then this one's going to correlate. And my red ones are all going to be 6. Notice that 2 over 12 reduces to 1/6. 10 over 12 reduces to 5 pi 6. 4 pi twelfths reduces to, or sorry, that's 14, reduces to 7 pi 6. And 22 over 12 reduces to 11 pi 6. So notice we don't really use the twelfths at all. Most people use the reduced form. So the red ones are all the 6. Okay, one more to go. The black ones. So I'm going to make black lines here. And notice how far that is from the x-axis. So in another one that would correlate would be that. See how it's going to be symmetrical? So this is going to be a black one. And then this is going to be a black one. These black ones should all be the same. And they're going to be all of your thirds. 4 pi over 12 reduces to pi thirds. And then this one's going to be 2/3, 4/3, 5/3. So notice it would be 0, 1/3, 2/3. This would be 3/3, but I didn't mark it. 3/3 would be one whole. 4/3, 5/3, and this would be 6/3, but we write it as 2 pi. So that's the unit circle. I know you're not going to believe this yet. This looks horrible. But by the time you get to calculus, you're actually going to prefer radian measure 2 degrees, if you can believe that, because it's so organized and it makes so much sense that when I say 11 pi 6, you'll be able to picture that, where if I said what that was in degrees, it would be a little trickier. So this is going to be kind of nice for this. Couple patterns to point out, just so you know how I remember them all. So this is quadrant 1. Maybe I'll write that super big. Quadrant 1. In quadrant 1, everything has a 1 in the numerator. So this is the 6th, the 4th, and the 3rd. In quadrant 2, ready for a cool pattern? the numerator is always one less than the denominator. So 2/3, 3/4, and 5/6. In quadrant 3, the numerator is always one more than the denominator. 7/6, 5/4, 4/3. And in quadrant 4, the numerator is always, this one's not quite as convenient, 2 times the denominator minus 1. So 6 times 2 is 12. So this is 11/6. 2 times 4 is 8 minus 1, so 7/4. You can think of that because you're almost at 2 wholes, but you're not quite at 2 wholes. You're a sixth away from 2 wholes. So it's 11/6. 8 pi-4 would be 2 wholes, so you're a fourth away from that. All right, this is just one explanation of the unit circle. Why do I care about this? Because now we're going to go back to our notes, and these are ones that I just need you to know. I need you to be able to look at 360 and say, oh, that's the same as 2 pi. That's all the way around. Pi-thirds, I need you to know as 60 degrees. I just realized that means we didn't actually put those degree measures in. So what would these be as degrees? Let's go ahead and write those in. Again, I'm not going to do the pi-12ths. This is 30 degrees, 45 degrees, 60 degrees, 90 degrees. This would be 120 degrees, then 135 degrees. See, I have to think about it. Hold on, 180 degrees and 210 degrees and 225 degrees and, wow, look at me struggle. See, I don't like degrees. 240 degrees, 270 degrees, 300 degrees, 315 degrees, 330 degrees. All right, I gotta go back and do this one. Oh yeah, 150. Okay, so now you have both the degrees and the radians on there. So some of the ones I'd like you to have memorized is 360, same as 2 pi. Pi-thirds, same as 60. Pi-fourths, same as 45. 90 is pi-halves. 45, pi-fourths. Use your unit circle to see if you can get the rest of these. And then come back and look. 30 degrees, pi-thirds. 360 degrees, 135 degrees, and 330, which is 11 pi 6. Okay, these are just ones that in the end you're going to have to know. I know it's terrible, it's so much information. You're going to have to know that whole unit circle. Now, of course, are we going to have things that are not on the unit circle? Yes, 1 through 8 here shows you all the ones that are not. So how do we convert? The same way you convert anything. If you had 3 feet and you wanted to convert that 2 inches, all you need is a conversion factor, which means you multiplying by something that'll cancel your feet and put your inches in. So what's the relationship between them? 12 inches are in 1 foot. This is called a conversion factor. Conversion factor. And then that gives you the feet cancel, and you get 36. Now the unit is inches. So our conversion factor for degrees and radians is using the fact that pi is equal to 180 degrees. So since that's not quite enough for everybody, I will actually tell you the equation. If you're trying to go from degrees to radian measure, then you want to multiply by pi over 180. If you're trying to go from radians to degrees, then you want to multiply by 180 over pi. But The basic conversion factor is this. And honestly, if you just know that, you can convert anything. That is your conversion factor. So I have degrees, so I need the degrees on the bottom so that they cancel. And I know that there's 180 degrees in pi radians. Notice radians doesn't have a unit, like a little tick or a circle or anything. An M, it has nothing. It's just radians, it just is. So you can go ahead and do that. People sometimes leave pi in the answer and sometimes they don't. It doesn't matter to me. I'm not going to do it for this example. So on your calculator, there is a pi button on your calculator. Make sure that you use it. 4.74 times pi and then divide by 180. And this is now in radians. Like I said, there's no unit for that. We just have to write the word radians. So again, this is in degrees. So if you want the degrees to go away, put it on the bottom so it'll cancel. And then the conversion factor is always pi and 180. You're either going to do the 180 on top or the pi on the bottom. Okay, times, I want the degrees to go away, pi over 180 times pi over 180. All right, I will give you the answers to the first 3 of these. And then I'm going to be looking for the 4th one so that I know at least once you did it on your calculator. So this one, go ahead and do that on your calculator and make sure that you can get that. Okay, now this one has a pi and it doesn't have a little degree symbol. That's how you know that it's in radian measure. There's no degree symbol and you see a pi in it. So I'm going to multiply by, I want to get rid of the pi. So I put the pi on the bottom. See how they'll cancel? And my conversion factor is 180 degrees is the same as pi. So I've converted. 5 times 180 divided by 11 is 81.818. And this does have a symbol, degrees. That's what's left, degrees. So I see a pi. I don't see any measure, so I know it's in radians. Is times 180 degrees, and I cancel the pi by putting it on the bottom. This gives me 864 degrees. Negative pi sevenths. So try and think about what that means. It's tiny, right? Pi sevenths. So if pi is halfway around, it's a seventh of that. It should be tiny. It should be a small number of degrees. And sure enough, if I multiply by 180 and divide by pi, then I get 24 or 25.714 degrees. So 1/7 of the way around. 20. Oh, that came out really bad, didn't it? 25.714. 25.714 degrees. And the last one, you can show me when I go to check your notes that you did it yourself. 180 over pi. The pi's cancel. Go ahead and get that answer for me. So now I want to talk about positive, negative, coterminal, supplementary, and complementary angles. Positive angles are generated by counterclockwise. So that means you're always going to start at 0 and you're going to go this way. And 45 is right in the middle. That's what 45 degrees would look like. You don't have to draw the rest of it. I was just doing that so you would see where I started. 2 pi thirds, you should be thinking to yourself, I'm going 2/3 the way around the half circle. Pi is halfway around. So 2/3 would be around there. 5 pi fourths. So now you're going to go 1 whole and 1/4. Not that I want you to just do this in your head. You shouldn't actually write it out. But I'm going to go 1 pi around, but then another 1/4. So that's there. But most kids just learn to recognize it on the unicircle, that all the fourths, this is 1/4, 2/4, 3/4, 4/4, 5/4. That's what it would look like. Negative angles just mean that they go the other direction. So when you see negative pi fourths, it means you're going to start here and you're going to go this way. So even though on the unit circle that we drew, pi fourths is right here, that's just a distance that it is from the axis. So now that you're going to go in the other direction, negative pi fourths is going to look like this. That's negative pi fourths. Negative 170, so here's some degrees that you probably know. 180 would be all the way to the other line. So we're going to do almost all the way. So something like that would show me negative 170. And I chose negative 2 pi thirds because we did do 2/3. So it's the same concept. This is pi. I'm only going to do 2/3 of that. I'm going negative. That's why I went underneath instead of on top. So it's going to be right around there. That's about 2/3 of the way. Coterminal angles are angles that share an initial side and a terminal side. So for example, if somebody said to you, draw a picture of 370 degrees, you might be confused for a minute because you would think, well, that's bigger than 360. And if I go all the way around, that's 360. So what does 370 look like? It's starting to go around again. So it looks like 10 degrees. So if you drew a 10-degree angle or a 370-degree angle, they would look identical, and we call them coterminal. We're going to do that same thing, but in the opposite direction. I'm going to start with a 35-degree angle, and I want to know what other angles would be considered coterminal with it. So I can find that really easily by just adding 360 degrees. In other words, I can start at 35 and then make a whole extra loop. So then in total, I'll have gone 360 plus 35. And that gives me 395 degrees. Now it does ask for one positive and one negative. You can get the negative one by going backwards. So again, if I start at 35 degrees and I want to arrive at that exact same spot, then I can go backwards, and that distance will be 360 minus the 35, which will give you 325. But since you've gone backwards, you want to mark it as negative. So another answer is negative 325 degrees. That would be if you started here and you went backwards. Okay, let's do the same thing for 210. 210 is right about, this is 180, so somewhere in here. Okay, 210. What other angle would look just like 210 if you went there from the negative direction? So the difference between the two, the 210 plus whatever that negative angle is, right? So we'll just call it x. Together, they would add up to 360. So you can say that x is 360 minus 210, which is 150. But to get there, you'd have to go in the negative direction. So negative 150 would, oops, that looks like 15. Negative 150 would look just like 210 degrees. Or you could find something that looks just like 210 by going around first. So I've gone 360. Now I'm going to go my 210. So I went 360 and I went 210. So altogether I went 570. Those are considered coterminal. Now, if this is at all confusing, generally kids just subtract 350 or 360 and add 360, and that'll give you the two answers. But I was hoping to make you understand why that works. So let's try that shortcut with the next one. I'm at negative 40 degrees, which means I've gone in this direction, negative 40 degrees. And if I do another 360 in the negative direction, minus 360, then I will have gone completely around. I'll land at negative 400, and that is exactly the same. But if I'm at negative 40 degrees and I add 360, so I'm at negative 40 and I go positive 360, I'll also land in the exact same spot. And that will give me 320 degrees. So both of those answers are the same. Are you ready to do it in radian measure? So now we're going to do the exact same thing, but we're going to add and subtract 2 pi. So I have pi halves, and I want to add 2 pi. So just like anything else, you need a common denominator, pi over 2. So 2 wholes is the same as 4 halves. And I get 5 pi halves. Where do kids struggle? With the fractions. So you do have to make sure that you understand how to get a common denominator. I'm at pi halves, and I want to subtract 2 pi. I do the exact same process, but with a negative. I get a common denominator, and that gives me negative 3 pi halves. So pi halves, I know you just learned this, but pi halves is right there at 90 degrees. And negative 3 pi halves is 1 half, 2 half, 3 halves. So it's the same. And 5 pi halves would be somebody going around all the way, 2 pi plus that extra pi halves. So those are my 2 answers. You can try and do it on your own for the next 2. Stop the video. That would be the best thing to do. But the 2 answers for the next 2 are going to come from doing negative pi thirds plus 2 pi, which is negative pi thirds plus, now we need to change it to 6 thirds. 2 is the same as 6 over 3, and that gives me 5 pi thirds. That's one of the 2 answers. And then negative pi thirds minus 6 pi thirds, so minus 2 pi, but I've already changed the denominator, would be negative 7 pi thirds. Those are my 2 answers for that one. And 5 pi eighths. So negative 5 pi eighths plus 2 pi. I need to change my denominator. And to change eighths, 2 into eighths would be 16 eighths. Minus our 5 pi eighths would give me 11 pi eighths. And then negative 5 pi eighths minus 2 pi. So 5 pi eighths, so if you think about this as being eighths, it's a little bit more than a half, although it's this direction. So it's somewhere around there, because that would be 4 eighths. So I'm somewhere around here, and if I subtract 2 pi, I keep going in the negative direction, I'll land in the same spot. Or if I'm here and I go in the positive direction, I also land in the same spot. Okay? But the long and short of it is, if you just add 2 pi and subtract 2 pi, you'll be good. 16 pi eighths gives us negative 21 pi eighths. And they are going to ask for a positive answer and a negative answer, a positive coterminal and a negative coterminal. 2 positive angles, alpha and beta. So this is the Greek letter beta. Remember, we already learned this one is alpha, little fish, are complementary if their sum is pi halves, or you might have learned it probably as 90 degrees. 2 positive angles are supplementary if their sum is pi or 180. So of course, you're already very good at this in degrees. So if you just say 90 minus 64, then you can find its complement is the complement. They complement each other. They add up to 90. So here's your 64, here's your 26. They're called complementary. Supplementary is when 2 angles add up to 180. So if you have 64, this one is going to be supplementary. But again, you find it the same way. 180 minus 64 is equal to 116. So that is the supplementary angle. So what you need to remember is when you're doing things with radian measure, the process doesn't change. The process is the same. You're just using a different value. So I still want to do 90, but I'm going to use pi halves. Pi twelfths. So pi halves minus pi twelfths, I need a common denominator. So I'm going to change this one to pi twelfths. so that they have the same denominator, and I get 5 pi twelfths. That is the complementary. And if you think about it, so pi halves is the same as 90 degrees. Complementary angles will add up to pi halves. So if you just have pi twelfths, but then you add 5 pi twelfths, that would give you 6 pi twelfths, which is a half. For the supplement, it's going to be pi minus pi twelfths. But you do the problem the same way. 12 pi over 12, you need a common denominator. And 12 pi minus pi is equal to 11 pi. So 11 pi twelfths is the supplementary. And again, a supplementary, 180 degrees, or pi. So if you just have pi twelfths, pretty tiny, but then you have the other 11 pi twelfths, that would give you a whole pi, which is what 180 degrees is. Okay, you should really try this next one on your own. I will tell you that the two answers are pi eighths and 5 pi eighths, but I will do them now. So to get the complementary, oh, I didn't label this one, supplementary. I'm going to do pi halves minus 3 pi eighths. I need a common denominator. So I'm going to make the pi halves into 4 eighths. 1 half is the same as 4 eighths. Minus 3 pi eighths is 1 pi eighth. You don't really need the 1. Which makes sense. 3 eighths and 1 eighth would be 4 eighths, which is pi halves, 90 degrees. And now I'm going to do pi minus 3 pi eighths. Again, I need it to be a common denominator, so I'm going to change this to 8 pi over 8 minus 3 pi over 8 is equal to 5 pi over 8. And that is the one that would be supplementary. Now, there are definitely some people saying, I can do this in my head. I mean, if I have 3 pi eighths and I'm trying to get to a whole pi, I must need 5 pi eighths. That's great if you can do that in your head. But some people struggle with fractions, so I was showing you how you could do it. Arc length. So arc length has a very simple formula. Arc length is if you have a circle, a radius r, and you have a central angle that intercepts an arc length s, then that means here's your angle, then the length of the arc, it's kind of like saying a piece of the circumference. So circumference is all the way around, but arc length is just the curve that's defined by this theta. So it has a really simple formula. There's only one thing that you need to know. You have to measure it in radians. This formula only works in radians. There is a degree formula also, but we're going to use the one for radians. I'm telling you right now, people forget this all the time. But if you're allowed to use an appendix and you don't have in big letters next to this formula, change theta to radians, and I can't help you with that. So I'm going to right away, I see that they're asking for the length of the arc, so I write down my formula. I fill in what I know. 27 inches is this, and theta. But it does say 160, which, by the way, if you're going to look at 160, since 180 is all the way over, it's a pretty big angle, okay? But we're going to change it to degree or to radians. Our conversion factor is that 180 degrees is the same as pi radians. So I can cancel those zeros, and 6 over 18 reduces to 8 ninths. So 8 pi over 9. You're, of course, welcome to do that on your calculator, but it was easy, so I did it in my head. But now I have to get out my calculator, and I get 75.398 inches. Okay, make sure that you have your unit. And you should think about that answer. If you have a circle and its radius is 27, it's pretty big, right? So if you go all the way around this far, not quite all the way, right? Only 160 degrees, then it would make sense that it would be about 75. Okay, next one. In a certain circle, the length of the arc is intercepted by a central angle of 240. And that arc length is 16.76. So they're doing the opposite. This time in your S is equal to R theta, they're giving you the S. So just be careful which thing they're asking for. But again, theta must be in radians. Can't stress this enough. So 240 is on our unit circle. It's one of the ones that you're going to eventually know by heart. But in the meantime, you can always convert. So the conversion factor is that 180 degrees is the same as pi. But I put the 180 on the bottom because I want it to cancel. So now I just get radian measure. I can also cancel the zeros. And 24 and 18 reduced to 4/3 if I divide by 6. So you can, of course, just do this on your calculator, or you could flip and multiply. So 3 over 4 pi to clear the fraction. But in the end, you're, I'm sure, going to get your calculator out anyway. And your final answer will be 14.001 inches. Notice that I'm always rounding to 3 decimal places just to keep us all consistent. Okay, last one. The sector of a circle is similar to arc length, but arc length is just the actual length of the outer curve. The sector is this whole area, okay? For a circle of radius r, the area of that sector is given by this formula, but again, measured in radians. It's really the only thing you have to remember. So a sprinkler on a golf course fairway is set to spray water over a distance of 70 feet, and it rotates through an angle of 120 degrees. Find the area of the fairway watered by the sprinkler. So 120 degrees would be bigger than 90, so something like that, because there would be 90, right? So bigger than 90, and it goes out 70 feet. So we want to find this area right here. So I use area is equal to 1/2 r squared theta. 1/2 r is 70, and theta, you do have to stop and figure that out. 120, my conversion factor is pi over 180. So now the degrees cancel, and the zeros cancel, and it reduces by 6 to give me 2/3 pi. Okay. And you can go ahead and plug that into your calculator, and you get 5,131.268 square. Make sure you got the square, it's an area, square feet. All right, you did it. You got through section 1. It was a big job, and I hope you have a great day.